Hello! In this video, we are going to prove the following theorem. Let a and b be real numbers. If 0 is less than a is less than b, then for all positive integers n, a to the power of n is less than b to the power of n. Okay, now before we get into the proof, we're going to use the following fact in our proof. Given any real number a, if a is greater than 0, then for all positive integers n, a to the power of n is greater than 0. Okay, now let's get into the proof. To start out the proof, let's give ourselves two real numbers, a and b, where 0 is less than a is less than b. And our goal is to show that for all positive integers n, a to the power of n is less than b to the power of n. And since we're trying to prove a statement about all positive integers, we are going to use induction. And so let's start with the base case. In the base case, we're trying to prove that this is true in the case where n is equal to 1. So really, we're trying to show that a to the power of 1 is less than b to the power of 1. Well, let's start out by writing a to the power of 1. Now, we know that a to the power of 1 is equal to a, and a is less than b, and b is equal to b to the power of 1. So as you can see, a to the power of 1 is less than b to the power of 1. So we have shown that this is true in the case where n is equal to 1. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer n where this is true. And the whole goal of the induction step now is to show that this is also true for n plus 1. So really, we want to show that a to the power of n plus 1 is less than b to the power of n plus 1. Well, let's start out by writing a to the power of n plus 1. Now, we know that a to the power of n plus 1 is equal to a to the power of n times a. And if we take this inequality and multiply the positive number a on both sides, we get that a to the power of n times a is less than b to the power of n times a. And also, since b is greater than 0, then by this fact, it follows that b to the power of n is greater than 0. So then, if we take this inequality and multiply the positive real number b to the power of n on both sides, we get that b to the power of n times a is less than b to the power of n times b. And this is just equal to b to the power of n plus 1. So as you can see here, we have shown that a to the power of n plus 1 is less than this, which is less than b to the power of n plus 1. So we have shown that this is true, where instead of n, we have n plus 1. And that was the whole goal of the induction step. So we have completed the induction step. And since we've completed both the base case and the induction step, this closes the induction. So we have shown that for all positive integers n, this is true. And so putting this all together, we give ourselves arbitrary real numbers a and b, where 0 is less than a is less than b. Since a and b were arbitrary, this means we have shown that given any two real numbers a and b where this is true, we have that this is true. So we have proven the theorem. So this completes the proof. And so yeah, that's pretty much it for this video.